Hello students, welcome to week 3. So let's do a very quick recap of what we have done last week in unit 2 on transmission lines. So we first considered transmission lines, which is just a pair of conductors bridging the source and the load in itself as an element to study when the speed of light delay is considered to be finite, right? So we notice that we cannot lump, as it's called, the performance of the pair of wires into a single component, but rather we would have to use a distributed model wherein each segment is small enough so that we can assume that the speed of light delay is insignificant within this small element, and hence we were still able to use ideal circuit elements like resistors, capacitors and inductors in order to model the entire transmission line. Then we took a very specific case where we said that instead of taking up the entire complexity of the distributed model, we remove all the resistive loss elements and just kept the inductors and capacitors to derive solutions for voltages and currents using just the inductors and capacitors. So we notice that we get the voltages and currents now functions of both space variable x and time satisfied the telegraph's equations, and these when combined and solved together leads to the wave equation. And we said that the solutions to these wave equations had a particular form that reminded us of waves, and we used this formulation for voltages and currents to derive something called reflection coefficients and transmission coefficients when the characteristic impedance of the transmission line is different from the terminal load resistances. Okay. So I felt like the last week was a bit mathematical. We dived deep into the derivations for the telegraph's equations themselves, and then we also looked at solving the partial differential equation of the wave equation to get the functional forms, tried to understand a little bit about the function themselves. So to begin this week, I felt we should probably take a step back and try to understand what these reflection coefficients are trying to portray, right? So if you remember, we had used the shy wave generator analogy to understand wave behavior, and this behavior is quite analogous to the behavior of voltages and currents on transmission lines, which is why it is used as a necessary tool to understand voltages on transmission lines. So I am going to try and mimic the reflection coefficient, the voltage reflection coefficient that we studied, specifically for those special cases where we had an open termination, a short termination, right? And we'll understand what those reflection coefficients mean, right? So let us start with this simple video for an open circuit termination. So very similar to the video that we saw for the definition of a wave, this time I am going to allow the video to go a bit further and actually see what happens as the wave reaches the end of this line and what tends to happen beyond that. Okay. So let me play that again. So notice the envelope of the beam bending as it moved forward, and it almost appeared as if it was coming back after it went all the way to the end of the line, right? So, couple of things that I want you to have observed in that video is, if I were to launch a shape, right, of the beam bending that looked like that, it reached all the way to the end of the line, and what came back was a shape that was very similar to what reached the end of the line, right? So, this is the behavior, right, for the mechanical wave. You can also assume that this is the same for the voltage wave. Now, we will see what an open circuit means in a transmission line and why the reflection coefficient was what it was, right. So, let us assume a generator connected to a transmission line of some length L, right. Now, I have launched a pulse at time t equals 0, and on this side I basically have a open circuit. All right. So, one thing that you can say about an open circuit is there can be no flow of current, right. So, essentially I at the load is 0, right. So, we know that the expressions for the current on a transmission line from the wave equation is V plus by Z naught minus V minus by Z naught is equal to 0, right, which means to say that V minus by V plus is equal to plus 1, right. So, if you remember, or if you can recall the expression for the voltage reflection coefficient that we derived last week, given a load resistance RL and a characteristic impedance of the transmission line Z naught, we said that for very large L's, RL's approaching infinity, gamma approaches the value 1, right. So, while that seemed very mathematical as a derivation from a formula that we got, it is akin to saying the same thing by saying that an open circuit does not allow any flow of current, right. So, while the voltage is sort of moving along the transmission line, when it reaches the open circuit, it notices that there is no connection between the two conductors, and which means that I can hold a potential across these two ends, but I cannot have a current flow, right. So, if I were to equate the current to be 0, I actually essentially get the same relation, right, of the reflection coefficient being 1, right. So, because the sign of this is positive, right, whatever voltage wave was incident at the open end of the transmission line, the voltage that is being sent back in the backward direction is of the same sign, right. So, this is to say the same thing as we saw with the bending of beams in the last slide, that if I had this sort of a wave shape going forward hitting the open line, right, I notice that the envelope that is returning from the end of the line also has the same shape, right. So, if it is all beams are bending one way, then the reflected wave also has the beams bending the same way, right. So, the same phenomena that you saw in mechanics, you can also apply it to voltages on the transmission line, right. So, how did I mimic the open circuit? In the mechanical case, I essentially did not do anything to the last beam, right. So, it just terminates abruptly, and the central wire is essentially freely hanging, right. So, it is allowed to rotate freely. Now, we are going to see the short circuit analog in mechanical waves. So, this time what I have done is, on the left hand side, I have essentially arrested the movement of the beam, right. So, I am not allowing the horizontal beams to freely move. Instead, I have put a clamp on this end and restricting the movement of the beam, right. So, when I do that, I notice that the envelope now has changed its sign, right. So, let us relook at the video again. All right. So, let us quickly summarize what we saw in terms of the mechanical wave. We saw that when I incident the beam bends that are moving to the left, which had a bump facing up, right. After it reached the clamped section, right, you noticed a reversal in the shape of the pulse that was going to the left, right. So, the pulse that went all the way to the left got reflected and came back, but you notice that the beam bending has reversed in its direction, right. So, you can think of the voltages that are being sent across a transmission line. Now, I am considering that the end of the transmission line is short, right. So, what can you say about shorted lines? That can we say something just like in the open circuit, we said that the current is 0 in an open circuit. What can we say for a short circuit? This time it is with the voltage, right. So, we can say that the voltage at the end of the line is 0, right. If I have a short circuit, the voltage is 0 between the two endpoints. Okay. So, this is similar to saying that V plus V minus, which is the net voltage along at any point along the transmission line. Now, here if I were to consider just the end of the transmission line, you can say that it has to be 0 at all times, right, regardless of what time it is in the movie that you are playing, as the voltage is moving from the source to the end of the transmission line. At all times, V plus V minus has to be 0, right, which means to say that V minus by V plus is equal to minus 1. This is also the reflection coefficient, voltage reflection coefficient as we defined it, right. So, rather than remembering a formula saying that gamma is RL minus Z naught by RL plus Z naught, and that for RL being equal to 0, you get gamma of minus 1, right, which is fine, but I think it's more easier to know that these limiting conditions or special cases for load resistances, one can actually picture in terms of the short circuit voltage or the open circuit current and setting them to 0, and you notice that the voltage reflection coefficient becomes quite natural. Right? So you don't have to remember whether gamma is plus 1 or minus 1 for short circuit or open circuit. It should be quite obvious to you.